Assalamualaikum warahmatullahi wabarakatuh. So this is a lesson for AC motor drive, part 1, SKEE 4433. So this is the content for this lesson, which is the induction motor drive, actually induction motor itself, and then the next topic is actually how we can use power electronics converter in controlling the speed of the AC motor. So basically, for this syllabus, we are more concentrated on how to control the speed of the induction motor. Okay, actually we have, for the AC motor, we have several types of motors, but for this syllabus, we are concentrating on induction motor. Why? Because this induction motor is the most widely motors type that used in the industry, and there are several advantages, okay, compared to the DC motor, which is the motor itself is very rugged, lower maintenance, more reliable to the DC motor in terms of the weight and also the volume. So it has a less weight and also a very small volume, so it can be installed in a very tight space. And in terms of efficiency also, it is much more better than the DC motor. And one of the most important features of the AC motor, which is the induction motor, is actually it can operate in a very dirty and explosive environments as compared to DC motor. So DC motor has some limitation where it requires a very clean environment to operate in optimum condition. Okay, and actually typically the induction motor in around 40 years ago, they are mostly used for the application that required constant speed. Why constant speed? Because at that time there is no power electronics that actually converter that can be used, okay, to control the frequency. As we all recall back during your basic machine subject, actually the most efficient way to control the speed of the AC motor, induction motor, is actually by adjusting the frequency input, the frequency supply of the induction motor. But at that time, there is no such converters, okay, power electronics converters that can do that, okay. And usually to have a variable speed, what we not currently, actually maybe past 10 years ago, so they are adjusting the voltage supply by using a transformer, okay, by using transformer to adjust the voltage supply. Yes, the speed can be varied by adjusting the voltage supply, but in terms of efficiency, it is not as good as when we control the frequency input. So this is actually the structure of your induction motor. So we have a stator and the rotor. So the stator is the static part in the motor where, as you can see, we actually wind up the stator with the phase, with the winding phase A, B, and C. So this is actually a 3-phase. And as you can see, the winding between phases A and B must be 120 degrees difference. Okay. Also, you can see between B and also C, phase C, 120 degrees. And for the rotor, we have two types of structure. The first one that we call square cage, and the second one is wound rotor. And this is the graphic representation of the square cage rotor and its physical, the real world square cage rotor. So this is the rotor, and then this is the stator, and this is the wound rotor. Okay, so this is actually the graphics representation, and this is the actual wound rotor. Okay, This is actually the principle of operation. So actually, if we may recall on how this induction motor is operated, is actually when we have a three-phase winding at the stator, where where all the phases are excited with a three-phase voltage, meaning that you have a voltage supply to the phase, and then the current flows inside the winding. Okay, so when we have the current flows inside the winding of the stator, so it will create a magnetic flux around the winding. And since this is an AC supply, three-phase AC supply, so current where the current magnitude is actually uh, varying with time, okay, we will see that the flux that induced around the winding will be, as we can see, like a running flux. Okay, so it's actually a rotating running flux inside the stator. So the speed of the rotating flux, the running flux there, that what we call synchronous speed. And this synchronous speed can be either defined in terms of whether you are using radian per second, or you can use rotation per minute. Okay, so this is actually the equation when you are using radian per second for pi f over p, and this is actually the equation when you are using RPM units. So 120 multiplied with the frequency over p. And please be note that this frequency is actually frequency supply of the voltage source, and P here is the number of pole. And sometimes you also will see that sometimes this NS is actually 60F over P RPM. And please be noted that don't be confused, because if you are using this equation, please make sure that this pole is actually, you are using pair of pole. Okay, so if you have 4 pole, meaning that pair of pole is 2. Okay, so please do not confuse. Okay, so cannot erase this. Why? Okay, so so when we have the flux, okay, induced in the stator, so it will actually induce the flux will in the stator will actually also induce a voltage on the rotor. So when we have a voltage induced inside the rotor, so the rotor will a current will flow inside the rotor. So the rotation, so the sorry. So the interaction between the rotor current and also the flux, rotating flux at the stator, so the interaction between this, okay, I rotor, and also actually we can also say that the flux here is actually proportional with IS, so we can say that the interaction between IR and I stator will produce torque, okay, will produce torque, which is actually Newton meter. So that is how the motor is actually finally rotating. Okay, so the rotation of the rotor we define as a speed of the rotor, which is omega r, and this speed of the rotor must be always less than the synchronous speed. And the difference between these two speeds, the synchronous and motor speed, is we call the slip speed, which is this equation, or this is in actually a radian per second, and this is actually in the rotation per minute. Okay, so the ratio between the slip speed and the synchronous speed is known as slip, which is S, and you can calculate the slip as equal to omega S minus omega R over omega s, and this is in radian per second. Okay, this equation is actually in radian per second. So we have almost complete on the operation of the induction motor, where we have already recall or refresh what is the synchronous speed, what is your rotor speed, and so on. So right now we will go on the representation of the induction motor in an electrical circuit. So this is actually a per phase equivalent circuit that represent the induction motor. So as you can see, we have, this is actually the stator part, okay? And this is representing the, what we call the air gap. And this is representing the rotor side. So each element, as you can see, is actually represent some, the internal resistance of the stator, okay? And actually RR is actually a rotor winding resistance and so on. So we have the currents that flow inside the stator and the current that flow inside the rotor. Okay. And this is the power relationship that is actually, this is actually the equation that power transferred from stator to rotor. So this is actually what we call the air gap power. Okay, so we have a stator, which is PS. So this is the power rotor. So actually the power rotor right now is equal to the air gap power. Okay, which is you can calculate by using this equation. And this power air gap is actually, we have losses, which is we call loss in rotor winding. Okay, this is due to the rotor internal resistance. So this is losses. This is actually losses, and the power output of the motor can be calculated by using this equation. So this is actually the power mechanical that you can actually calculate, which is this one. If you want to simplify, is actually equal to 1 of minus S multiplied with the air gap power. Okay. The power of the motor can also be calculated in terms of mechanical output, which is you can calculate the power motor is equal to the torque produced by the motor multiplied with the speed of the rotor. Okay, and this speed of the rotor, as you can recall, is actually can be written in terms of 1 minus S omega S. And when we actually replace this, so we will actually eventually we will got this equation, which is the power of the rotor. Okay, power of the rotor, the input of the rotor is equal to the torque produced multiplied with omega S, and we rearrange this, so we will have this the final equation here. So this is actually the equations between the relationship between the torque and also the speed. And this equation, as you can see, is a nonlinear equation. So when we plot the torque versus the speed of the motor, we will have this graph, which is a nonlinear graph. So actually at this part, this is, we can consider this is actually a nonlinear, and but after this, though, from this to this, we can consider this is a linear graph. Okay, so this is the torque produced by the motor, and this is the speed of the motor, where the speed is 0, and this is the synchronous speed when your omega r is equal to synchronous speed. And as you can see here, when the motor in a standstill, so it requires a torque value to actually to start rotating, and the torque maximum will produce when the slip is equal to Sm. So how to calculate Sm? So this is the equation to calculate the maximum slip that give the maximum, sorry, the slip value that give the maximum torque. Okay, and this is the speed when your speed of the motor is equal to your, sorry, is equal to your synchronous speed. And as you can see, if omega s is equal to omega r, you will see that there is no torque produced. Okay, and sorry, this is where the torque rated here, so, and the speed rated. So please be noted that our motor will always operated within this area. So meaning that your motor is always very close to the speed of the synchronous, because this is the point where your motor will operate at highest efficiency, lowest power factor, and highest power factor, and so on. And please be noted that this is the slip. So when your omega, your speed of the motor is 0, so the slip is 1. And where your omega motor is, the speed of the motor is equal to synchronous speed, the slip is 0. Okay, so power electronic converter in AC drive. So in modern AC drive system, the speed of the motor is controlled by controlling the magnitude of the voltage supply and also the frequency of this voltage supply. So this can be achieved by using inverters and also incorporated with the DC to DC converter. Okay, but mostly inverter will play the main role in the AC motor drive. Okay, and there are two most widely used inverter, so which is the 6-step voltage source inverter. So this one is actually a square wave, and another one is the most advanced, which is the PWM voltage source. So please be noted that the speed of the motor is controlled by magnitude and also the frequency. So this slide will actually, the objective of this slide is actually to show how by using the 6-step voltage source inverter, we can control the magnitude and the frequency of the input of the AC motor. So this is actually the basic configurations on the 6-step 3-phase voltage source inverter. Okay, so right now, please be noted that to control the speed, the first one is the magnitude, V, AC, and the second one is the frequency of the VAC. Okay, so as you can see here, for example, we have a 3-phase here. So this one, you cannot control the frequency and the voltage supply, the voltage magnitude cannot be controlled. So you need to convert into a DC first, because you are using the inverter here. So you are using a control rectifier. So by adjusting the fire angle, definitely you will have a variable VDC. So VDC is a variable. So meaning that you can control the DC input to this inverter. Okay, and so this control rectifier will control the amplitude, while the inverter will control the frequency for the AC motor. Okay, so this is actually the square wave. This is a 6-step 3-phase. So this is for the line to line voltage, and this is is actually a phase voltage. Okay. So the frequency can be varied by adjusting the period of the switching state, okay, by adjusting here. So you can actually adjust the timing of the switch, okay. And the second method is actually the what you call the Pwm 3-phase. So as you can see, we are using the same configurations, but right now, both the magnitude and the frequency are controlled by PWM inverter. Okay, because why? Because PWM, you can adjust the V output, which is the fundamental, by adjusting your MA. Okay, so this is your V1. So this is actually the line-to-line voltage waveform, and this is actually the phase voltage. And as you can see, the variable output voltage can be achieved by adjusting the modulation index or the modulation amplitude. And the frequency can be varied by adjusting your frequency sinusoidal, which is your modulating frequency. Okay, so that's all for part 1. So we continue for part 2.